Everybody. Today I'm going to talk about the work that we did in Alaska when I was at Anglo Gold between 2002 and 2006. And for me, it was an exciting period of exploration. I had to learn a lot. I'd never worked in the tundra before, particularly that close to the Arctic Circle. Come on, why won't the slide move? Okay. The area we focused on in Alaska was gold in the Tintina belt. The Tintina gold belt. It's an intrusion-related set of gold deposits that run from the Yukon in Canada right through Alaska up to just beyond Fairbanks. We had two projects there. One was called the Gobi project, which was adjacent to the Pogo mine. At that stage, Pogo wasn't a mine yet. And the other is the Livengood project. The Pogo project continued through till Anglo abandoned Alaska in 2005 and 2006. And the Livengood project was given to the manager for North America at the time, Jeff Pontius, and they continued working on it through a company, the junior company they formed called International Tower Mines. And today, International Tower Mines still exists, and the Livengood project has gone through a pre-feasibility, and they're sitting with a relatively low-grade 0.7 gram a ton ore body, but they've got 8.97 million ounces in the ground. And they are quite confident they're going to get that thing moving in the next year or two. But it was the end of the era in Anglo Gold. At that stage, around about 2005 and 2006, virtually the entire top echelon of senior geologists in Anglo Gold walked out. There were many reasons for it, and one is that there was a change of senior management, and Anglo Gold's view of greenfields exploration in particular was very low. They wanted to buy projects rather than find them. And I was rather concerned because when I left Anglo Gold in 2006, I was never replaced. Now, it didn't worry me in any other way that I felt very strongly about geochemists. Then I discovered that many other mining companies had no longer got chief geochemists. And in Canada was a rather renowned Canadian geochemist. He's actually the godfather of world geochemistry. He was a consultant. And if anybody's ever used Amos standards, Barry Smee was the guy who accredited them. So he's a fairly eminent fellow. And I wrote to him saying I was very concerned about the demise of geochemists. And his reply to my email is something I've never forgotten. He said, however, the sad fact of life is that the regulators know when reported data, are not compliant to stated best practices, and consequently, many reports are just a joke. The legal entity 43101, now 43101 is similar to our SAMREC code, it's a Canadian mining code, and they refer to a competent person as the QP, or a qualified person. If something goes wrong, he said, is a QP is responsible for it all. But the more important point was that he said that the geochemist category is being phased out the lexicon here in Canada. And there are few of us left, and no schools producing applied geochemists, and few schools actually have any courses at all. Those of us who remember the 70s and the 80s will remember that there were three great schools of geochemistry in the world. One was Queen's University in Kingston, Ontario, Colorado School of Mines under Graham Kloss, and our own Cape Town University School of Geochemistry. And to the best of my knowledge, the last student produced by Cape Town was in about 2002 or 2003. So we don't really have trained applied geochemists anymore. Anyway, I was very concerned about this. And if you look at this particular graph here, what I've got here is a primary search method for gold at the prospect scale since 1900 to the present day. What was the way they found to drill the first borehole? And you see this area in green here? That's the role played by geochemistry. It's always been a major component of gold exploration. The other major component of this blue area, which is the prospectors. But you notice their role has died out as time gone by because no longer are gold deposits easy to find. The persistence that they used to have is now controlled by stock markets. They were unregulated in those days. Today, everyone is regulated. And in their day, the drainages were unpolluted. It's one of the big problems we have in geochemistry is that streams are badly polluted by all kinds of things, notably fertilizer. So that is the basis on which we went to Alaska. The area we worked in Alaska is this Fairbanks area. There is the Arctic Circle. This line running south here is the border between the Yukon of Canada and Alaska. And this area here that we worked in here is a Paleoproterozoic area of rocks that run between two major faults, the Denali Fault in the southwest and the Tentina Fault in the northeast. And in between these two faults are the areas that we were interested in. There's the Canadian-Alaskan border. There's Fairbanks. There's a town of Whitehorse. This map is produced by Piercy et al. In 2016. It's not actually a gold map. It's a map relating to lead zinc deposits, but it's the best one I can find that show the rocks. And the most important rocks to us are these Neoproterozoic to Mississippian, and for those who don't know American geology, the Mississippian's early Carboniferous rocks. These are continental margin assemblages and they schists and gneisses. And this is a very old map produced by Goldfarb in 1997, but I like it because it shows what we were dealing with. Here is Fairbanks over here. Our Gobi project was down here, and this line here is 50 kilometers, is down here. And the one project we had, the Gobi project, was right adjacent to the Pogo deposit. And our Lavengood project, and the one that still exists this day, is up here in the north of Fairbanks. There were two mines in the area at that stage of importance. One is Fort Knox, which was the sort of the mine that started this all. And then Pogo came in around about 2006, 2007, at the end of our era in Alaska. This here is what Fort Knox looks like from the air. It's a heap leach operation. There's the open pit. It's a fairly mature operation. They've got two heaps. And in typical American style of mining, they put a big primary crusher. They're quite amazing things to see. You're right on the edge of the open pit, and then move whatever they have to move around towards the mill and then to various heap leaches. Now, if you look at this, is a fairly low-grade deposit. I mean, this is really low grade. When you consider we're mining 7 grams a ton at Far East, this is 0.36 grams a ton, but they've got a fair tonnage of ounces. And today, heap leach works particularly well in getting gold out of these low-grade deposits. But it's mostly in Paleoproterozoic schists of primary sedimentary origin. It's bounded by the north of the Tentina Fault system and on the south by that Denali Fault. And as in all these Alaskan deposits, the plutonic origin is ascribed to the gold, which occurs in veins and vein swarms. And in the case of Alaska, they're fairly disseminated. But this one, it's not. This is the Pogo deposit. You'll see there are actually two major veins that they mine. And this mine is now owned by Northern Star, who bought it from Teck Sumitomo in 2018. And this is a fairly good grade deposit, 10.8 grams per ton. And again, it's in gneisses and schists from Proterozoic to mid-Paleozoic age. And here they've actually dated the mineralization at 104 million years. The gold again is in sulfide veins, but the important part of this is this bismuth tellurium component, which helped us in exploration, and we therefore introduced a system of multi-element analysis. It was still in its early years, but it worked very, very well for us, and I'll explain it to you in a minute. But you can see Pogo runs at a fairly high grade compared to Fort Knox. It's 13.6 grams a ton, and it's 4 million ounces, but they have two single veins rather than a whole lot of disseminated veins. So this is the sort of background in which we went into Alaska. And my job was applied geochemistry. I was working on several projects at the same time in Peru, in Colombia, in Brazil, in Russia, and also Alaska. And there was also quite a lot of work that we were doing around Marilla in West Africa. So I was kept fairly busy. I actually spent most of 2002 to 2006 in an aeroplane. This geochemistry started in 2002 when I was handed a whole lot of data, and I'll show you the data in a moment. And what we discovered was the first problem we had in Alaska was substandard laboratories in Fairbanks. The point here is that these substandard laboratories weren't just any fly-by-night operations, they were the major commercial labs. And there were two of them that performed extremely badly, and it had nothing to do with the lab management. It was a peculiar thing, and I'll explain it to you in a minute. The other components was improving assay quality and QA/QC management on any project that I work at any time in my life as a geochemist. I spent a huge amount of time on this. And that includes laboratory auditing. I've probably audited about 300 laboratories since I worked in this field of exploration geochemistry. The other component is when you're dealing with operations like this, particularly in remote areas, sample handling, sample logistics, and laboratory turnaround are key. So that has to be managed and facilitated. And I spend a lot of time doing this rather than having a geologist go and fight to the labs. I do it for them, and that way we work far, far better, and we got what we wanted. But then there was the actual work, and this is what I'm going to focus on today. It's just there's improving soil and stream sediment sampling techniques. Now I'm going to show you a stream sediment sampling technique which has sort of died. Actually, I've never published anything on this, and I should do, because it is actually an extremely good way of prospecting for gold. And I did a lot of evaluation of soil sampling, which meant understanding the tundra regolith. And then the last bit, which is I seem to spend most of my time these days working on, is evaluation and reverse circulation drilling. It has its own problems with sampling, and if that sampling is not managed, you can produce, particularly with gold, can produce the most awful results with it. Anyway, this started off with this invalid geochemistry of the rock samples. What happened was the gold assay fraction did not match the sample fraction for multi-element analysis. The sample will be divided into two. You'll see this table, there's a red line going down it. This is the gold that's sent off for assay, and this is all the multi-element analyses. Those are two separate fractions. We got the results back that didn't match, and I'll show you in this table in a minute exactly what I'm talking about. But when we went back and looked at the reserve portion, which are consulting geologists, we employed a team of consulting geologists to help us in the field. When we went back to look at the lab pulp sample numbers, they did not match the sample numbers that we had in the field. All field rock IDs were correct. We've actually ground truthed everything. And clearly, two consignments of rock samples have been badly compromised by sample numbers, and sample fractions have been jumbled. And if you look at this data, there's data here for a quartz vein that has the composition of a gneiss, not a vein. And if you go through this data, you'll see that there are three samples. One's a quartzite, one's the other two are schists, but they've all got roughly the same geochemistry. There's another three, two schists and a quartz vein, all the same geochemistry. Another quartz vein with the geochemistry of this lot over here, and one of them has got high gold, and all three of these samples have got high gold. And if I never looked at Anglo-American research laboratories, I would have never understood what happened. The same thing happened with a bunch of samples we brought in from Saudi gold mine in the early days to Anglo Labs, field samples. I brought them in, and I discovered the same pattern in the analyses. What the crusher house had been doing, and I don't know how many years they've been doing this, but they've been crushing one sample, and instead of putting that sample into a single sample bag, they put it into the next three samples. So you did this would be sample one, but these, which are sample 2 and 3 in actual fact, would be given the pulp of sample 1. And they never even bothered to crush these two samples. And so it went on. And this is exactly what was happening in here. Anyway, we went into this laboratory and I audited it. Well, this is the laboratory where crosses are, all kinds of things. And Ed Cadle, who knows me well and who's known me when I've audited laboratories, knows I freak out when I see cluttered laboratories. Laboratories should not be cluttered. In fact, Ed being here, this is the SGS lab in Johannesburg, where Ed actually worked. Look at it, it's organized, it's tidy. This is what our lab should look like. Not this clutter with ladders in the way, benches, dust. The dust levels, this place has never been dusted. And when we caught operators splitting a sample from like this, this is not, you do not split a sample like this. A hopper is a device to split a sample in half equally. So you use the whole width. You don't pour the sample down the middle of it, especially from a piece of foolscap paper. Anyway, we did a full investigation, and I was hugely impressed with the commercial laboratory involved. They brought in senior management, and together we audited this place. And when you're in a remote place like Fairbanks, and particularly in the US, you find all kinds of things. And what we found in this laboratory was that somehow they'd employed their friends from Fairbanks, and it was a nest of drug addicts. Cocaine users like you cannot believe. They had to fire the entire staff. Okay, so that was the first thing. Then, because we were using a variety of commercial labs and we were employing this new multi-element technology, we needed to test it. And this is SGS, ALS, all offer it. It's a 48-element technique. In the early days, We didn't know what his performance was like. We've since found it's probably the most useful analytical technique in explorations to be produced. What it is either an aquaregia or the one I prefer, which is a 4-acid, which uses 4 acids to dissolve the entire sample. It's called a total digestion. And then using a combination of optical emission spectrographs and mass spectrographs, we're using using an inductively coupled plasma introduction of the sample into the instrument, we can get these hugely accurate analyses, or they're very, very good. And I'm not going to go into detail of these graphs, but I assessed the whole lot of them at 3 laboratories using these 5 or 6 highly specialized samples, produced about 8,000 graphs, and gave both the techniques a complete bill of health, and found the only thing that contributed to the variation of the sample was the sample itself and not the analytical technique. So we applied all this technology in Alaska, and off we went. And the very first thing we did was start looking at the Gobi project, which is the one next to Pogo. This is a drilling operation on the hill. All of this operation, I worked with helicopters. To me, the most powerful transport tool in geochemistry is a helicopter. There's our chopper there. In this case, we're using a Bell Ranger. This is what the schists look like that host the gold. And the very first thing we did, here's the Gobi project, here's Pogo Mine. In this particular area of Shaw Creek, we did a stream sediment orientation study. And that was introduced to introduce this new technique of stream sediment sampling. Stream sediment sampling on gold is based on the assumption that you get places or nuggets of gold in drainages. That's here, and as the years have gone by, the gold has got finer and finer. And we introduced, years ago, probably in the 50s and 60s, the -80 mesh technique of prospecting for gold. But in my view, it was a hit and miss method. There's a far, far better method for prospecting on gold, and it was based on the microscopic studies that I did at Anglo Research Labs. And it's totally independent of us. 2 other geochemists, a guy by the name of Guy Fletcher, who was with the British Columbia Survey, and Richard Mazzucchelli, an Australian geochemist, started to develop similar approaches. But this is the one we developed in Peru, where it's first worked. But it's based on this model. If you look at this table here, you see all it is a microscopic study of 1,002 gold grains in a head sample. Now, working in Anglo Labs, we had access to a metallurgical laboratory, so we could actually get head samples to do this. So this is a Val Reef's head sample, and I measured all the gold grains I could find in that head sample until I got to 1,000. And one of the grains there counted for 96% of the grade. So you had 1,000 grains, and only one of them, because it's the biggest of the lot, and you use volume calculations, this is the volume of the sphere, to do this. And you discover that you've got a lot of gold grains, but you've got only one grain that accounts for a lot. And this is what it would look like if it was in an alluvial deposit, and that square is 1 millimeter. They're quite coarse. And they are very difficult to find. Because there's just one here and one there. And if you put them in a sample together, as we did in this case, we found something unusual. When we moved them, they formed little sausages, but that is actually 2 grains, so you make them even bigger. And when I put one of these grains in a scanning electron microscope, I found that the mill had actually enlarged the grains. So you're making the problem even worse. So you've now got a pulped rock with coarse gold in it. And this is what happens when you've got coarse gold. This is the model. This box here is a 5 kilogram geological sample. It's very likely at the grades we're dealing with to have 2 gold grains in it. Now we are going to crush that up, make a pulp, fine grain pulp, and we're going to assay the pulp. These little pictures are each of a fire assay crucible of which you put 30 grams in. The chances of you doing 18 analyses and getting the grade that you want is 1 or 2 out of 18. That is how we calculated it. So you're actually going to, if you do 1 analysis on a stream sediment sample, you are likely to have 1 chance in 18 of actually hitting the gold in the sample if it's there. So we decided that there must be another way of doing it and go for the fine gold. And we discovered it was a very, very sensitive technique, but it required very careful sample collection. It's very labor intensive, but it works. We use it in the Andes, where the guys got to climb up quite steep slopes to sample. It can use standard assay techniques. We used ALS laboratories in Peru. We used the ALS, that's MS61, and this was in early 2000s when it was still in its early days of development. We could also do aquaregia gold rather than fire assay because the gold is fine enough and is liberated. It is actually a low-cost technique, despite it being labor-intensive, and it has few logistical problems once we worked out how to do it. And it requires screening to minus 75 micron in the field and using a flock unit, and the river water is not guarded. So in other words, the water is kept until all the gold is got out. That's the finest, the fine gold. In Peru, in the Andes, we're collecting up to 10 samples a day. This is how it's done. You screen into a bag. Having been associated with De Beers people, the screen is based on the screens that De Beers have been using for years. We use a drum clamp and I make the screen out of a Teflon pipe. And this is us screening in the field. And there is a fine fraction, minus 75 microns. The little Coke bottle over to one side there contains Magnafloc, which is the flock unit. You put a capful in there, it separates everything out, and that is the fraction that gets sent to the laboratory. It gets set in that little Tupperware container with still with the water in, and then the lab will dry it. They will dry the sample, and that is how it goes to the lab. That's what we did in Alaska. We took it along to Alaska and we tested it. But before that, I had to do an orientation study. I had no idea how the drainages worked, so we used the chopper. And that's the areas I showed you earlier where we actually operated. And this is the kind of model that I use for working out drainages. You have first, second, and third order drainages, starting at the top of the slope, working downwards to the major drainages. And there is it done from the air. This is the Corder Creek, Shore Creek area, which was on the map. And I did a full analysis. There were dozens of these photographs produced. And you will see that wherever you look, we've actually been able to understand the drainages. To see them from the air close up is much easier, and you can therefore identify areas where to sample, like I've done on this photograph. Today I would use a drone. I don't think I'd use a helicopter in all cases. And we marked the areas where to sample beforehand, and the crews would just go to those grid reference points. It also required looking at the sediment in the drainage. Now this is the tundra. This is where there is not much rock weathering. There's not much sludge in a river. We've got to struggle to find the stuff. And a lot of it is glacial dust, which is a lower type of loess, which actually contaminates both the soils and the stream sediments. And we had to find a way of getting a suitable sample to send to the laboratory. And these two geologists, Ryan Cross and Steve Hovis, they're a consultancy that we use, Northern Associates. They work very well with us. And they screened in the field and sent quite a much larger sample to the local laboratories for further screening. They don't have the labor in the US that we had in Peru or anywhere else. But this was where we hit the jackpot. The USGS got an anomaly very close to this. It was about 6 or 7 meters away where they got their sample at 20 ppb. Using our technique, we got 556 ppb. And throughout the whole area, in general, our anomalies were at least 20 times bigger than the conventional minus 80 mesh sampling that they use in the rivers. It also required a lot of dealing with these meandering drainages, because here the profile of the sediment is more contaminated by this glacial dust than the slope. So to work out where to get the best sample was a major undertaking. And you can see we land this chopper in the riverbed, and this area here is where we just get this very small amount of sediment that would be sampled and screened. And that is how we did this. It took me about 2 weeks to work all this out, and then we put the crews in and they went off and sampled. It's not easy to locate the sampling sites, and I think the most important point I need to make is this dilution by loess, glacial loess. It obscures anomalies. And sampling has to be done at the time of the year when the flow is the slowest. So often you're working early in the season when the thaw sets in. That was a very useful study. We got a lot of good data from the stream sediment sampling, and quite a lot of anomalies from that went on to be sampled by soil sampling. But the story here is much more interesting. This was more of an adventure than a technical soil sampling exercise in the end. But this is what I'd be doing. I'd be investigating each soil, the pits that we'd make, and they'd have 3 kinds of sample. It'd be a rock or chip sample, be a mattock or shovel. This is a mattock. The American call this a mattock. And they have a very nice shovel, which has got a quite narrow for digging nice little holes. But you can see what the soil looks like. It's full of bits of rock. And this, you are walking on a carpet of moss. The whole country is covered by the soft moss. It's like walking on a carpet. But in some places, the soil is quite deep. And we decided probably the best place to sample. This is a profile. Here's the moss, here's the soil, and here's the bedrock. That might be the best place to sample is here and use an auger. Somebody with augers that they mix the sample up. They tend to act a bit like a cement mixer. So we did 2 samples to test, again, orientation studies, an auger sample and a shovel sample to see which was the best. And we produced these maps. I'm not going to go into show you exactly how they worked. But my major problem was the way they compared bismuth to gold to tellurium, because they've got different values. Bismuth is much lower than the gold, and tellurium is considerably higher than the gold, and so many other. So I replotted the stuff, and instead of plotting the values, I plotted the percentiles. This is how I plot data, because then you can compare copper, which runs at 2 to 300 ppm, against gold, which runs at 1 to 5 to 10 ppb, and we found that the anomalies now become absolutely more identical. There are the copper values, and there are the gold values. This is the map they originally gave me, and I was very unhappy with it. I was also very unhappy with the way they sampled, because they don't stick to a grid. They change the grid direction, so the sampling becomes biased. I prefer to always keep the same orientation when doing soil sampling. It stops you missing or misunderstanding the anomalies, because if you look at the later development of this, I don't unfortunately have the slides here, I'm still in Alaska. The best anomaly is actually not shown on here. They found it later. If they'd sampled properly, they would have found it much earlier. This is a story I want to tell you, which was the most amazing thing that I've ever had happen while on a soil sampling exercise. I don't know if anybody's ever read this book, Chicken Hawk. It's about the chopper pilots in Vietnam. They're probably amongst the bravest of the brave, these guys. They fly towards a and cool guns down into the war areas. And if you go to YouTube, you'll see the Rolling Stones song, Give Me Shelter, played while these choppers are flying into action. It's the most amazing sight to see these choppers going. But anyway, this is what happened. I was actually doing a soil sample evaluation here. I was working with this chopper. This is an R44 chopper. It's a bit smaller. And the guy standing in there is a guy by the name of Tommy Thompson. He's a Vietnam War vet. He flew these choppers in Vietnam during the Vietnam War. Delightful man. A guy that he was very unassuming, but can this guy fly a chopper? What happened was, in 2004, and I've got the maps of these Alaskan fires taken from the satellites. And here, they were bad in 2004 and 2015. The muskeg and the forests catch fire during the summer in Alaska, and this is what they look like. They are huge fires. They make our fires in the Western Cape look like small bonfires. And this is what kind of stuff you're dealing with. You can see in the background. And these are the rescue choppers. They've got special rescue choppers. We got a call that there was a fire here on this particular project. This is our ER drill project. The field camp is down low. I don't have a photograph. It's down low of the hill. But as you see, as you go down the hill, there's forest and moss. Here on the top of the hill, there was nothing. And this is what it looked like in the fires. Same field camp. We got a call. This is the Pogo mine. Around the mine was, just to show you what these fires look like. And this is the fire taken from the camp by the 2 geologists who were on the site. We had to go and rescue these 2 guys. And this is what it looked like. And you'll see here the skeleton that was after the fire had run through. These guys are in serious danger. I had the camera. I was sitting in the chopper passenger seat, and I got opportunity to see what it was like to fly in Vietnam. With us in the air were 2 young rescue pilots who'd never seen this kind of service. And they wouldn't go in. They could not go through the smoke, which is in this photograph here. And the way we went in was, he said, this is how you do it. And he took the chopper right down the side of the hill, and he went up the side of the hill like this, and he landed. Now this chopper is smaller than they had drill ranges, and we had the smaller R44. We put the guys in and we flew out. And to me, this is the most amazing flying I've ever seen. As we went up the hill, you can see us going here. The trees are just underneath the chopper in this heavy smoke. We landed and we picked these guys up, and this is what it looked like the next morning. So someday soil sampling gets very, very interesting. The other work that we did was, once we found these gold anomalies, we started drilling, and we put in RC drill rigs. You can see everything has signs, everything's designed for snow. I learned to ride one of these things. They're quite fun. And this is the drill rig, and these are my last two slides. One of the big problems I have with RC drilling is the cyclone over here and the splitting. They normally split, they take a meter sample, which is about 50 to 70 kilograms, and they split it through a series of riffle splitters down to 12%, 12.5%. My problem is that the riffle splitter is this wide. I showed you in the labs again. Is this wide, and this thing just drops the stuff straight through, as you can see in the next slide. So just they're not using the splitter. And the other problem is I'm making dust. Dust dilutes the matrix, and what I've worked over the years, I've discovered that the sample loss due to dust from the beginning of the sampling operation with RC drilling to the end of the assay in the lab, they're losing up to 10% the sample, and they're actually enriching it in gold, which is not really a good idea, because particularly if you're using RC drilling for resource estimation, you can overestimate the sample slightly, and it creates biases, unnecessary biases. So I spent a lot of work on the RC rigs. We redesigned these whole things based on the Australian rigs, which are suitably done. And at the point that we pulled out, we were actually going to bring in one of these current splitters. I don't know what happened after that, because we left the whole particular project. And that more or less was the end of my days in Alaska. Today, you can see there's Livengood, our Livengood project. There's Fort Knox, there's Pogo. This is the area that we worked in. But you can see as you cross the border into Yukon, there are a huge number of gold deposits that have suddenly developed these yellow areas, including the Capstone Minto deposit and the Western Copper deposits. So in the end, Tower Minerals took over the Livengood project. It's a great promising project. As I said, it's 8.97 million ounces, but there's still no mine. And that's a long time now, 15 years without the mine starting. And I think it's a low grade that gets investors worried. And the large Gobi project eventually became a JV between Running Fox Resources and Anglo Gold Ashanti. And there's nothing there anymore. The Canadian Stock Exchange, there's no more Running Fox Resources. And I can see no evidence of any work going on that particular project. And that is the end of my story. Thank you very much for listening. And if there are any questions, I'm prepared to answer them. Thank you.
Thanks, Keith. It was great.
Well,
Thanks.
videos and microphones on again, and we can take questions for Keith.
Thanks, Keith. So my quick question, and first of all, you didn't let me introduce you, but I think your fame and fortune precedes you, so we won't introduce you now. But when I hear your presentation, Keith, how many gold mines have actually been missed out there?
John, this is my problem. One of the things that when we went through the presentation last night, I cut out a lot of the talk. One of the things that concerns me is that geochemistry plays a huge role in gold exploration. But there are so few geochemists who have got the experience in gold exploration that one is wondering that they're not walking over these things. The most successful people in gold exploration at the present time are Chinese.
They stopped the system.
Sorry?
I'm just going to mute you all again because we're getting interference from people discussing in the background.
Tomorrow again. I'll ask.
Someone's.
Let's just unmute Keith again. Keith, just unmute.
Okay, there we go.
There we go.
I have unmuted. Can you hear me?
Yeah. There we go. Yeah.
Okay. My problem is, and I think Ed will bear me out on this, is there are precious few geochemists left in the world, particularly ones who've got the background or the training in understanding the various ways and areas in which prospecting is done. The basic methods that they still use, soil sampling and stream sediment sampling, rock chip sampling, haven't changed. We might have refined them, but in the end, we're still looking for gold. But what has really enhanced the work that we do is the various analytical techniques that we've developed. And one is the level of accuracy which we can now assay for gold down to 0.01 part per billion, which is hugely, a very small amount of gold. But if you're looking for an anomaly.
Okay, carry on. We've got you.
If you're looking for an anomaly, the only way you are going to find it is to sample and assay, sample and assay. And what happens with these projects is they have a budget meeting and they say, how far have you guys got with this project? You say, we're still doing the soil sampling, or we're still doing the stream sediment sampling. And the next question is, haven't you started drilling yet? You can't just drill these projects. There's a lack of persistence. And this is because of all these projects are investor driven. The number of junior mining companies that run out of money way before they even develop a project is huge.
Okay.
And this is where the problem lies. People do not understand that you, to find gold, you actually got to be persistent.
Guy Fremantle has a suggestion on how to check labs. Guy, can you talk to us? Unmute yourself.
Hello, Annie.
Hi.
Just unmute yourself, Guy. There we go.
Okay, can you hear me now?
Yeah, thanks. I thought that was fascinating. I just missed the first 10 minutes, but one of the ways that we dealt with the labs is it was a project in Namibia. We went to an abandoned mine nearby and got a few hundred kilos of their tailings. It was the Khan mine, if anybody knows it. And we then split that up and we inserted those as our own sort of CRM, because the labs can recognize a CRM and they can recognize blanks, and they also recognize the pattern in which you insert them. So we figured out a way in Excel how to give our homemade sample a random number, so the lab never knew, and it looked like ordinary rock. And we used that to just make sure that we were getting believable assays. Have you ever done something like that?
No, the whole world's changed since then. First, all the labs, you want to use certified reference materials, because that is what the stock exchange demand. So to use a homemade standard is actually unacceptable, because it will vary itself. It has its own nugget effects. These standards, which are prepared like the AMOS standards, the standards used by Geoscientists, those they've actually been accredited by a qualified accreditor, somebody like Barry Smee. So what you do is a whole new process of doing this. The labs will recognize that you can stand in your head. They will recognize a standard. And in fact, they are too busy to worry about that. I can promise you. The big commercial laboratories, and Ed Cadle will bear me out on this. I mean, I've audited 300 labs. I know exactly how they work. If you put in standards in there, they can recognize them. That standard will be recognized because it comes in a sachet, whereas your sample is a rock or it's RC material. That standard has to go in there. And you have to put in at least 10% of your samples have to be that standard. 5% have to be blanks, which is really the best standard. That is your hidden standard, the blank. That is the only standard, and that you also can buy now. That is guaranteed blank, and that also can be certified. And then there are the various duplicates. There's the pulp duplicates, and the lab recognizes those as well. And then there's, of course, crushed duplicates as well. So you've got all those things. So you're sitting between 20 and 25% of the samples that the lab are assaying for you today are actually QA/QC materials. That is how strict they are. So if you put in a hidden standard, I'll put a stop to those type of standards, homemade standards, in early 2001 already, because they actually they haven't been properly homogenized. And that is the issue. A standard has to be properly homogenized. So you will find now there's a company called Rock Labs in New Zealand, which makes a standard where they actually do not use natural gold. They actually they take a blank pulp and they add gold to it. And that thing is what the labs use as a lot of their standards. And those things are highly repeatable. The commercial standards, their repeatability is also quite high. I've got all the data for all the AMOS standards. They are darn good considering, but they screen those things so fine that only the fine gold goes in there, so they get no nugget effect. The trouble is with standards that you put in from your own source, unless they're ultra pulverized, you will have a nugget effect. So you'll get a variation in grade.
I get that. We had all the blanks and we had duplicates. We had drill site duplicates, pulp duplicates, but we just put our own one and it was slimes. And that's why we thought it would work, because it was fine already, and it was very consistent actually when we got all our results back. But it's interesting that it's not used.
When you consider that ALS, Joburg at one stages and SGS are analysing, they analyse almost 1 million samples a year. They haven't got the time to work out who's got standards and blanks and cheat. They do not cheat. And let me tell you, if I catch a lab cheating, the whole industry will know about it, and they will not get custom, and they know it. So don't expect, this is not the old Anglo research labs where they were a law unto themselves, those old company research labs. That can't happen. These are commercial labs. They are there to make money, and they got to keep their integrity. If they get caught, and they've been caught on many things. You know, I've had labs have their websites hacked by clients so that they can actually see what was on the project next door. This happened in Canada.
Well, come on, Keith, that's like the good old days. I mean, we need a bit of life and spice in this industry as well. Otherwise, it gets boring. And Adrian, are you?
You know, I could give it.
Okay, let's get some other discussion. What about Adrian? Let's get Adrian's input on gold exploration and how he would be doing it. Are you there?
We didn't do too much stream sampling in Mali and West Africa in general. But I mean, I agree 100% with Keith. You've got to understand what you're doing. And so many people just go through this, oh, well, everybody does it this way, and they don't check up the QA/QC properly. And labs always know when you're sending a standard in. They know where the blanks are because obviously they're rocks as opposed to pulps. But I mean, we've generally found dealing with SGS or ALS or whoever it is, when you point out a problem, they're quite happy to look at it with you and say, yeah, okay. I seem to remember it was either Lula or Marilla. We found there was a definite undervaluation of about 5% when you look at all the standards, and they were quite happy to repeat those. And that's when we went to doing the gravity finish rather than AA on any samples above 5 grams a ton. So we just had this procedure. If the AA result came back at over 5 grams a ton, then you repeated it using it a gravity finish. But yeah, I agree. There's a tendency for a lot of geologists not to understand geochemistry and not to want to understand it, similar to geophysics sometimes. And I think a lot of stuff has been missed. I'm working with a company at the moment in the Golden Triangle up in Canada, in BC. And boy, there's so much stuff around there that in the past people have looked at, walked over, and you come around 10, 20 years later, look at their data, and things don't work for you. Yeah.
Mm-hmm. Fantastic. Okay,
George Henry had a hand up.
Okay, and then we'll go to Ed Cable. Thanks.
Thank you very much for an interesting talk, Keith. You mentioned that you did some work in West Africa around Marilla. Now, were you trying to do the stream sediment sampling in that area?
No.
Just soil sampling?
No, Marilla was a totally different exercise. It was actually a research exercise, and sadly it was never finished. Again, one of the things we found with Marilla is that the composition of the biotite in the rock, you see, I had access to electron microprobe. In Anglo we had everything. We discovered that the composition of the biotite in the gold-bearing rocks compared to the non-gold-bearing rocks, which are identical, is different. The magnesium-iron ratio is different. And we never got to the bottom as to why that is, because that's quite an important piece of information to use if you want your drilling, to actually look at the biotite, to actually target where the gold will be and where it won't be. That's what we did. But most of the work I did in West Africa was working on mapping the regolith and developing techniques of understanding the various components of the regolith in terms of the residual, the erosional and transported and the positional environments of the regolith, and dividing the geochemistry up in those terms. And also the role of mapping RAB holes and working out where the transition with the redox boundary is in the laterite, all those kind of things. And that kind of data, it's a huge amount of data again, and normally a lot of the operation geologists don't have the time to actually assess that data. I spent a lot of time assessing that data. And let me tell you, on Sadiola, there was some amazing stuff, really, really good stuff. And I will argue that there are deposits around Sadiola which they still haven't found.
Okay.
Because that is hiding a whole story.
Thank you.
Okay, let's have Ed. Ed, we've had a lot of comments made about laboratories. Do you want to chip in from a lab point of view and your years and years of experience in running labs?
No, I think what Keith has come up with is spot on. It certainly is the way to operate, and
Just
I agree.
adjust your screen a bit. We got half your face.
Oh, I'm sorry. Is
There
that
we go.
better?
Yeah, you look much better now.
Thank you.
Sorry, Ed, you're gone.
Am I gone?
No, you're there, don't worry.
Keith, just an interesting one there. You were talking about the association of bismuth and tellurium. Did you pick up anything on the arsenic antimony front?
Keith?
Keith, can you hear that? I think he's gone frozen.
Okay.
No, it sounds like it.
We'll give him a minute. Oh, Keith.
Calling Keith.
Keith. Ground control to Keith.
I'll run up the street quickly and wake him up.
You're just down the road, are you, John?
Yeah, we're 3 houses down the road. So we've got.
While we wait for Keith, what is the sort of standard these days for making sure that the guys collecting the samples remain honest?
I'm sorry, Henny, I missed that.
I'm saying, how do we keep the guys collecting the samples honest these days? What is the accepted standard method of putting in a check?
No, you've got me on that one. I've been out of that scenario for the past 12 years, so I'm not sure what the current situation is, Henny.
What was it in your day?
You mean when actually sampling in the field and submitting those samples through to the lab?
Correct.
Oh.
Keith.
I recall way back when I was an exploration field assistant. Some of the guys would sit under a tree and sample all around the tree. So we had to, to bring in a check system. When put traces in and they were numbered, and and we advised the laboratory, which ones they were, or they would, or check both sides. It checked that the laboratories were doing their job and also that the guys collecting it were doing theirs. So I'm just saying, has that evolved into something more finer these days? Maybe the guy who just spoke to us just now can enlighten us on that one.
Maybe Guy can. I can't. I do recall the story about sitting around a tree collecting samples as opposed to following grid lines.
Henny, I worked on a project in Gabon many years ago where we got access to the UNDP data for 1 in 200,000 sheets. So big project, and kind of halfway through taking their data and making some sense out of it, when we started hearing this story about, well, you mustn't believe any of that stuff because the geologists, well, not the geologists, the soil samplers used to sit under a tree and just collect from there. But when you actually process the data, and you look at the copper and zinc and iron and so on, these things follow the geology. They follow the different units. You can map a 1 in 200,000 sheet just by looking to some extent at the geochemistry. So, we then said, well, there might have been a few people sitting under a tree, but the majority of the work, and it was a big regional study, the majority of the work is valid because it ties in with the geology. The other thing is the what do they call it? The chain of custody now. After the Briek scandal, you'll see the reporting in the 43101s. They're very precise about how samples were taken, how they were transported, how they were stored in the camp, how they were treated there in any way if they were treated there, and then from there on how they were carried to the laboratory. And you know, it's that chain of custody to make sure that people aren't salting along the way or whatever. So it is generally quite rigorous. You know, when it comes to people cheating, there's no ways you can keep up with them. But I would say it's, you know, very seldom done these days. And if guys are sitting under a tree, well, yeah, I guess you'll catch most of them. But it's human nature to do that kind of thing with certain humans. And if you look at the data properly, you'll see where something is wrong. I mean, Briex was a great case. If people had looked at the geochem data, they'd see that it didn't fit any sort of normal or log normal distribution. It was all over the place because the guys salting it were just pouring in grains of gold in the places that they thought might be a good idea, but there was no natural distribution to it at all. So you look at the data properly, which is where geochemists come in, and you know, you'll pick up that kind of thing.
Yeah, Adrian, I think you make a key point. Sorry if I can butt in there, Ed. I mean, it goes back to knowing the geology, doing the basic geology. You know, if you've done the geology, even if there is cover or regolith, you know, and you get out there and beat the rocks, I think a lot of those things can be overcome. You know, it's when you sit in front of a computer screen and never actually get out in the field, which I think is part of the problem these days. You miss the geology, and without the geology, you're going to run into problems.
Yeah, no, right. I concur with Adrian in terms of traceability and so on. Once you've collected the sample, then it's an easy matter of keeping track of that, the batch of samples that are then submitted through to the laboratory, so that there is a chain of custody from that point. In the actual field where you're collecting samples, unless you've got somebody overseeing individual sample taking, that is an issue, and this comes back to collecting the samples around a tree instead of actually following grid lines. Is Keith still away at this point in time, John?
Yeah, I just spoke to him. I think his system is bombed. So I said I would pass on the hard questions to him, and I'll run up the road with a piece of paper a bit later, and then he can respond to people who are asking the hard questions. Right. But have we got any other general points for discussion? It's been a good one, and I must say credit to Keith for a short, stimulating presentation.
Yes, John, I'd like to thank Keith for an excellent presentation and some very good ideas in the situation of collecting samples. I think it's a brilliant presentation. Thanks very much indeed. It's just the bismuth tellurium story. If you could follow up on the arsenic and antimony, that'd be great.
Okay, I'll get them to respond to you.
Right, thanks.
And any other questions, guys? Any?
Basically, I just want to sort of set the record there that not all the guys get lazy out there. I was one of the guys, I can recall, working for De Beers with my landy out, and then you've got a grid that you've got to maintain. They pre-decided where you're going to, and one of the samples was, I recall very vividly, was on top of a koppie at, you know, next to the trig beacon.
Is that the one you had to walk up, Henny, and it was in the hot midday sun?
No, then I decided I'm going to drive up there. So I actually said to the guys, look, this is a voluntary trip, and they all stuck initially with me. But as we went up, the TS started abandoning. They started bailing off the back of the Land Rover until it was only me and the guy next to me because he couldn't get out. He was inside, so ended up at the top, took the sample exactly where it should be taken. You know, so apart from then us writing on the maps BFR, and then head office would come back and say, what kind of geology are you talking about now? And we say it stands for big flipping rocks, you know, stuff. Anyway,
everybody, I'm back.
Okay, let Keith, Ed had a few comments. In fact, the most important one is he really appreciated your excellent presentation. Ed, do you want to chip in and ask about the other question?
Yes, thanks, John. Hi, Keith. You talked about bismuth and tellurium. What were the patterns with arsenic and antimony? Did they follow similar trends?
All three, that was the big problem when I showed those maps, is the arsenic values around that neck of the woods are quite high. They're sort of in excess of 1,000 ppm, and so are copper. Whereas the tellurium and bismuth are sort of fractions of ppm compared to that. They're about sort of 100. That's why I work with the percentile maps. And that multi-element data, it's the only way to work with it, is to convert everything to percentiles. And I've got software that does it, plots the stuff. I used Geosoft Target to plot it, and you get the most amazing maps. The trouble is you've got so many maps, and the only way to actually look at them properly is not on a screen, but actually print them. So you need a big printer. So you can lay these maps out and then draw them with a pencil. The visualization on the screen narrows everything down too much. You actually need a big A0 sheet of maps and lots of them.
Right.
And then you can actually map out these things and then georeference the marks that you put on the map. And you see the most amazing things come out, and they can direct the geochemistry, which this is what's not being done. Is the geochemistry and the geochemical prospecting is not being directed to the most promising areas. It's almost being done blindly. The worst case scenario is in Amazon and Brazil, where they just put down grids. You know, that's not the way to do it. You've got to actually target the areas a bit more accurately, that and use the geology and understand the regolith. If you don't understand the regolith, and particularly the guys in Mali, they know how much regolith mapping plays in actually understanding the geochemistry. Then when you've got the geochemistry and all that multi-element data, you've got to subset it so you can actually use it, because the dispersion anomalies for some of these gold deposits is actually surprisingly small.
Keith, we just
Right,
made that.
thanks very much.
Keith, we made that point exactly, that unless you get out there and do the geology, you know, grids have limitations. So all of this goes back to the point you made too. You've got to get on the ground and hit the rocks, you know, or deal with the regolith. You can't just do it from a laptop in a distance. Anyway, that was a very stimulating talk. Good stuff. Any other questions?
Can I ask a very simple layman's question? You said, Keith, that in Alaska, there's a lot of dust and a very little weathering of the rocks. Doesn't that upset the sampling?
It does. It's tremendously upsetting. You see, that's glacial dust. That's the stuff the glaciers grind off the rocks underneath, and then it's dispersed all over the place. So a lot of the dust that you're dealing with doesn't actually come from where the sample comes from that you're taking. So it obscures things. So you have to work out which part of the sample is going to be least affected by that glacial dust. The other thing you have to do is to map the glacial dust like we did with the regolith in Mali. That's where I learned a lot of the stuff, was working in Mali. It's no longer a laterite, it's now a glacial terrain, but the same principles apply. You've got to identify the...
And how do you separate it?
And then do the...
How do you separate the glacial dust from the others?
Well, first of all, you map out where the glacial dust is. So the samples that are badly affected with glacial dust, you know that. So you've actually got to go down and sample the bedrock, not the glacial dust. That's what we use the auger for. Okay. And you've got a sample right at the bottom. So you don't just take a pit. You know, often, and this is a lot of geochemistry is done in South Africa. We were terrible at it. I mean, they were sampling around Barberton, and every pit was the same depth, same place. Sometimes it was the overburden was very thin. So they never took that into account. Thin overburden over rock outcrop and thick overburden is two different environments. They should be mapped out. But it was only in the case of laterite where we actually got it right. And that was because of the work done at Saro in Australia by people like Charles Butt and Ravi Anand, where they actually started to understand the laterite. And then we took those principles in, which we used in laterite, and we took them everywhere, and learned to subset the environment, the sampling environment, so that we could actually use the geochemistry over areas where the bedrock is close to the surface is quite different to where there's thick overburden and might be like glacial dust diluted with alluvium. So
Keith, you've been mapping the glacial striations to then get a direction from where the hinterland, from where it might be coming from. Wouldn't that be an aid in your exploration?
No, not in Alaska, because you can actually see the glacier. You know, you can see where it's coming from. And we can't, we know where the glaciers are. I mean, a lot of the stuff is outwash as well. And when these glaciers recede in the summertime, the summers are quite dry in Alaska. This dust that's left actually blows and forms sand dunes. I can show you pictures of sand dunes. I'll be getting an arrow. And just covered with moss.
Interesting. Okay. Any more questions, folks?
Okay, thanks. Right, I think we've run out.
Okay, and you've got the tape, Penny. You taped it successfully this morning.
Yes, we've got it there with all here and there a little bit of a hiccup where the fine gold was edited out by the cloud, but I think the major part of the speech was there, and it's going to be available for the next week or so, guys.
Yeah, and Keith, you happy to distribute a PDF of your talk as well?
Yeah, can I distribute that PDF? I just need to edit out one or two things in case I'm pointing fingers at people. I don't like pointing fingers at people.